Happy Saturday, scientists! Wow, what a reaction to today's videos, and the product is subscribers. No, that's terrible. On the list of bad chemistry jokes with you. Nonetheless, today we are discussing reactions. C3 is our topic, the final topic for paper 1 in chemistry. Let's begin. C2 taught us that elements can react to form either ionic or covalent compounds, but how do we know what the structure of that compound will be like, how that reaction will happen, and how we can even go about naming those compounds? Well, there are some simple rules that we can follow in order to get this right. So let's begin. Before we get too far, we need to know about some essential elements that are found on the periodic table. These are our diatomic elements. Whenever we're confronted with a new topic that has an interesting name, it's a very good idea to see if we can break down that name in order to figure out what it's talking about. If we take a look at this name, we've got the prefix di, which we hopefully remember means two, and then atomic might lead us to think about atoms. Therefore, diatomic elements are likely to be elements that come in groups of two atoms. And that is essentially what they are. These are elements that are always found in groups of two in nature, and you can remember them using the phrase, "I have no bright or clever friends." While this may not be the kindest of phrases towards your friends, it does help you to remember that iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, and fluorine always come in groups of two. So if you're ever looking at an equation and it says that fluorine or chlorine reacts with something, you know that what was actually reacting was Cl2 or F2. Next, let's get into how we go about writing these formulas. We need to recall some general rules. Elements are proper nouns, and that means that they will start with an uppercase letter. Their symbols will also start with an uppercase letter. For example, in the case of chlorine, you would have Cl, not lowercase c, and then uppercase L. In fact, if you're looking at an element, or a series of elements in a compound, every time you see a new uppercase letter, you know you're dealing with a new element. When you're looking at a compound, the second part will change the ending of its name, usually to "ide". So, for example, carbon dioxide. Let's talk about how we go about naming our compounds. Covalent compounds first. In these, we use the prefix to indicate the number of elements that are present, or rather the number of atoms of each element. The prefix mono will indicate that there is one atom. Di will indicate that there are two atoms. Tri will indicate that there are three atoms. And tetra will indicate that there are four atoms. There is also just simply no prefix, and that will also indicate one. An example of this would be carbon dioxide. If we look at this compound, carbon, there's no prefix, so that means there's one atom of carbon, and then the di tells us that there's two, so we would write O2. And the 2 is a subscript, so it has to be lower down from the O. So you would never write CO2 with the 2 taking the same size as the O. It has to be a subscript. For your ionic compounds, we don't have prefixes to indicate numbers. Instead, we need to remember that ionic compounds need to be neutral overall, and therefore we can go about this by balancing the charges. Let's look at an example. If we look at lithium chloride, we know this compound has to be formed from two atoms, so we would find that lithium being a group 1 metal, will have a charge of +1, and chlorine, being a group 7 or group 17, will have a charge of -1. That would mean that those two charges cancel out, and the formula would be LiCl. A different example now, if we do lithium oxide. Lithium would have its charge of +1, but oxygen has a charge of -2. In order for this compound to be neutral overall, we would need a second lithium atom in order to cancel out the two negative charges on oxygen. Therefore, the formula would become Li2O. There's another special case in that some metals are known as polyvalent. And this means they have many charges. For your polyvalent metals, you're going to indicate the charge with Roman numerals in brackets. For example, lead 2 chloride. Now there is another way of getting to these charges that is a little bit more simpler perhaps than this idea of balancing them. Let's look at the example of lead 2 chloride. This tells us that Pb has a charge of 2+, and we know chlorine has a charge of -1. Now we could think about this and say that 2 chlorine atoms would be needed to balance out that 2+, but we can also do what's known as the crisscross, where we ignore the charge and we move just the number down and over, considering that there's an invisible 1 there for chlorine, and that becomes Pb with the invisible 1 that we don't bother to write, Cl2. This also allows us to reverse the charges. If we looked at this, we'd move the 2 back up, and that tells us the original charge on lead in that compound. This will become quite important later on, so do practice this skill of being able to reverse the charges from the chemical formula. Before we can move into writing our equations, we need to understand something known as the law of conservation of mass. Again, we can take a look at this term and see if we can understand what it might mean. Conservation would mean keeping something the same, and in this case, that thing that we're keeping the same must be the mass. The law of conservation of mass states that the mass of the products is equal to the mass of the reactants. And that is really the total mass on both of these sides. And this is only true in a closed system. So if, for example, your reaction produces a gas, then you need to have a stopper on the flask that contains the reaction in order for the mass of the gas not to escape. And you can do reactions to prove that this is true. We now have enough information that we can begin writing chemical equations. When we're writing equations, we will often write them in either word form or symbol form. Let's look at a quick example that we've used above, the production of lithium oxide. We would have lithium reacting with oxygen, and together they will react and form lithium oxide. We make sure that the elements that were present as reactants are also present as products, and that we show that they were added together to form a reaction, and that the reaction did happen using the arrow. We can also convert this into symbols, so lithium plus oxygen, and here we remember that O2 is a diatomic, so we need to show O2 and not just O. And those will react to form lithium oxide, and we've already worked out that that has to be 2 lithium atoms to cancel out the -2 charge on oxygen. We need to apply the law of conservation of mass to this in order to create a balanced symbol equation. We can extend the law further to mean that the atoms are conserved during the reaction. What that means is that these two oxygen atoms that we started out with here must also be present in the product side. There are two methods that you can use for rapid balancing of equations, and I'll go through both of them here for the same reaction. To begin with, you can start by creating a symbol and/or a color for each of the atoms that are present, but remember that when oxygen is in a group, or when the element is in a group, then that group is sealed together. You can't just have one single oxygen there. And the same would apply on the other side. So the two lithiums and one oxygen come together as a group and cannot be separated out. Next, we go about trying to make sure that the same number of symbols and of each symbol appears on both sides. We could begin, for example, with the lithium. We know that if we have to end up with 2, we must start with 2, so we would add a second lithium there. Next, we can look at the oxygens. We begin with 2, and therefore we must end with 2, but we cannot just put an oxygen there on its own. That oxygen has to come as part of the compound, because the compound is there all together. And that will put our lithiums back out of balance, and we will need to balance them by adding more on the other side. You can then come and create a total for that reaction. There were 4 lithium atoms that reacted with 1 oxygen atom in order to produce 2 molecules of lithium oxide. Let's look at the same reaction again, but with a different method for balancing. In this method, you start by drawing a line down the center, and on that line you add all of the atoms that are present, trying to end with oxygen. You then go and see how many are on each side, and then you begin balancing from the top to the bottom, starting with the side that is lowest. So on this side, lithium is lowest, so we would need to add a second lithium here, and we modify that change in our list. Now we move down, because the lithiums are at this moment in balance, and we look at the oxygens. They're out of balance, and we need to bring them up to 2, and in order to do that, we would put a 2 there. Now our oxygens are up to 2. This 2 does affect the oxygens, but it also affects the lithiums, and so this has now changed to 4, and we need to reflect both of those changes in our list. Now we start back at the top checking again, and we see that the lithiums are out of balance. We need to get this to 4, so we change that to 4, and we reflect those changes in our list. Those changes do not affect the oxygens, and they remain in balance. We can then go and write our final answer in, that 4 lithiums were reacting with oxygen in order to produce 2 lithium oxide molecules. Either way you go about it, you will end up with the same answer, and eventually you may have enough skill that for relatively simple equations, you can do them on your own, without actually writing out the symbols. Do remember though that there's no reason to get any of these balanced equation questions wrong, because you can simply count up your answer to make sure that the elements are equal on both sides. There is another type of equation that we are sometimes called upon to write, and those are ionic equations. Ionic equations will show the ions that are present and what happens to those ions. In order to recognize ions, we need to be on the lookout for this symbol next to an equation, AQ, meaning dissolved in water, which means the compound will have separated into its ions. Let's look at the reaction between hydrochloric acid and sodium hydroxide. That reaction will form sodium chloride and liquid water. The first type of equation is known as the complete ionic equation, and it will show every ion that is present. We'll have H plus and Cl minus. Both of those need to still have their aqueous symbol next to them. Those are going to react with sodium and hydroxide, reacting to make the sodium and chloride ions, as well as liquid water. And we can't separate out the liquid water into its ions because it is present as a liquid in the solution. This would be the same if you had, for example, a precipitate, a solid formed from two liquids. You wouldn't be able to separate that out into its ions either. The next type of equation is known as the net ionic equation, and that means it only shows the ions that have actually reacted. The chlorine ion has not changed on both sides of the equation, nor has the sodium, but the hydroxide ion has formed part of the compound. And the net ionic equation for this would then just only include those ions that have reacted and you can see that the net ionic equation is much simpler, and it tells us the interesting bit of this reaction, that hydrogen and hydroxide ions reacted in order to form water. That was the essential bit of information that we needed from this equation. Now that we know about naming chemical compounds and writing equations, we're one step closer to some more advanced chemistry. But before we get into that, we need to understand generally about how reactions happen, and for that we need to understand the difference between endothermic and exothermic reactions. Hopefully you remember from biology that the prefix endo means internal, and that exo means external. We would remember that thermic, of course, will have to do with temperature or energy. This can lead us to a definition. Endothermic reactions will take in energy from the surroundings, and exothermic reactions will give off energy. In an endothermic reaction, the temperature will go down, but the amount of energy in the products will be up from the reactants, because the energy has been pulled into the system. That will lower the temperature of the surroundings, but will increase the energy that is present in the system. In an exothermic reaction, the temperature will go up, but the energy that is present will go down as the energy will have released, and that's what caused the raise in temperature. We will show this using what are known as reaction profiles. The reaction profile will show the progress of the reaction and the energy that is present in that reaction. You'll begin by placing the reactants at their appropriate energy level on the graph. From there, the graph will increase to what is known as the activation energy. The activation energy is the energy that's needed for the reaction to happen. All equations, all reactions will have a certain amount of activation energy that is needed in order to break the bonds in A and B in the reactants that you are using. And then you will finally come and put the products at their appropriate energy level. The difference in energy from the reactants to the products is known as the energy change of the reaction. In this case, we can see that the energy change is positive, and therefore the reaction is endothermic, because the energy of the system of the reaction has gone up. In an exothermic reaction, you would see that the energy change would be negative, and that would be indicative of the exothermic nature of that reaction. If you are taking the higher syllabus, you will need to be able to calculate these energy changes using the bonds that are present. Let's look at an example of this. Let's look at the reaction between nitrogen and hydrogen in order to form ammonia. We need to make sure that we begin with a balanced equation, and in this case 3 molecules of hydrogen will be necessary to produce 2 molecules of ammonia. Next, we need to understand what bonds are present in this reaction. We know that nitrogen will form a triple bond with itself, and that hydrogen will form a single covalent bond with itself. The ammonia molecule, of which there are 2, will be formed with a central nitrogen that is bonded to 3 hydrogens. We can now go through and find the energy related to each bond type. So in this case, we'd be looking for the energy from 1 of the nitrogen to nitrogen triple bonds and 3 of the hydrogen to hydrogen single bonds. On the other side of the reaction, we would have 1, 2, 3, but 2 molecules of that, so 6 in total, nitrogen to hydrogen single bonds, because there is no difference between those 3 individual bonds. You'll be given a table of bond energies, and so you can then look those up. 945 kilojoules per mole for the nitrogens, 436 kilojoules per mole for the hydrogens, 391 kilojoules per mole for those. In total, we have 2253 kilojoules per mole of energy in the reactants, and in the products we have 2346 kilojoules per mole. To find the overall energy change, we do products minus reactants, and therefore the overall energy change in this reaction is negative 93 kilojoules per mole. This indicates that the reaction is in fact exothermic, as that energy has gone down overall the reaction, as the energy has gone down while the reaction happened. When you're doing these calculations, make sure that you are understanding which bond types are present. We now have enough information that we should be able to start to look at different types of reactions and how those reactions occur. We'll begin with the classic reactions between our acids and alkalis. Before we do that, we need to understand the pH scale. And we should remember that this was a scale that indicated whether or not something was acidic or alkaline. And it did so generally on a scale from 1 to 14, where 7 was considered to be neutral, anything less than 7 was acidic, and anything higher than 7 was alkaline. If you take the higher syllabus, you need to know that the pH is related to the concentration of hydrogen in solution, and you need to be aware that it is a change of a factor of 10. Changing from a pH of 1 to a pH of 2 means your concentration of hydrogen has gone down by 10. So there's more hydrogen at the lower end of the pH scale. With this information, we know that a neutralization reaction is trying to react an acid with an alkali in order to make that neutral solution, or that pH of 7. And there are 3 types of neutralization reactions that you need to be aware of. The classic reaction is an acid reacting with an alkali in order to produce a metal salt and a molecule of water, and that water allows the solution to be neutral. The classic example of this would be hydrochloric acid and sodium hydroxide reacting to make the metal salt sodium chloride and a molecule of water. The next type of reaction is an acid reacting with a metal in order to produce a metal salt and hydrogen gas. And you would prove that hydrogen gas is present using the squeaky pop test, where you put a lit splint into the test tube containing the gas, and if it gives that squeaky pop, you know the gas is hydrogen. Classic example of this could be hydrochloric acid reacting with a piece of magnesium to form magnesium chloride and hydrogen gas. These equations aren't balanced. And the final type of reaction is an acid with a metal carbonate, and that reaction will make a metal salt, carbon dioxide, and water. You need to be able to recognize the reactants in each of these cases and to be able to decide from those reactants what the products are going to be. The next type of reaction we are going to look at are redox reactions. Redox reactions are so called because it is a reduction reaction and an oxidation reaction happening at the same time. Let's look at the reaction between aluminium and iron oxide. In this equation, the aluminium will become aluminium oxide, and the iron will end up as a solid metal. We can spot the reaction in terms of oxygens for reduction and oxidation. Here, the aluminium has gained oxygens, and this means that this is the oxidation reaction, or a gain of oxygens. We can then also spot the reduction equation because there was a loss of oxygen. For those of you who take the higher syllabus, you'll need to be able to do this type of reaction in terms of electrons, and for that you'll need to write what are known as half equations. Let's use the same reaction. In order to write our half equations, we'll need to examine the charges or the oxidation states that are present in this reaction. If we look at aluminium, it is a solid metal and therefore has no charge, and the same would be true of our iron on the far side. In this compound, iron will have a charge because it's part of an ionic compound, and we can use crisscross to reverse that charge. So in this case, a charge of 3+ is present for both iron and aluminium. Next, we write out the equation to show how those charges changed. So aluminium went from no charge to a charge of 3+. And iron went from a charge of 3+ to no charge. We will now need to balance out the equation in terms of its charges. If we look here, this side of the equation has no charge, but this side has 3+. To cancel out the 3+, we will have to add electrons, and we'll need 3 of them to cancel out that 3+. The same would be true here, that 3 electrons will need to be added in terms of this reaction in order to cancel out the 3+ on the iron. We know, because we've previously established it, that the reaction going on with the aluminium was oxidation, and the oxidation reaction produced electrons or lost them from the aluminium, and so we can say that oxidation is a loss of electrons. We know that the reduction equation required the use of electrons, and it is therefore a gain of electrons. I like to remember this, that the R in reduction indicates that the electrons are a reactant in this type of equation. So the reduction equation requires the electrons that were produced in the oxidation equation. And that's why these two equations are always coupled in redox equations. We can apply this in the case of electrolysis. And the first thing we would use electrolysis for would be for molten salts. The reason we would use a molten salt is because the molten salt would allow the ions to move. And this is essential for electrolysis. But what exactly is electrolysis? Electro would indicate to us that electricity is involved. And hopefully we remember that lysis means breaking up or splitting apart. And so therefore this would be splitting something apart using electricity. Let's look at an example of splitting up lead bromide. If we were to turn this into a liquid, we would be able to split it up into its constituent parts: lead metal and bromine gas. Remember that bromine is a diatomic, and so therefore it will be shown as Br2. You would need to be able to write this in terms of what is happening. So you need to once again look at the charges. Here, lead would have a charge of 2+, and then a charge of 0. We have Pb 2+, and it will have to react with 2 electrons in order to form Pb. At the same time, bromine will have a charge of -1, but there are 2 of them, and they will react to form Br2. That's the other way you could get to the 2, is you need to keep the atoms balanced in this equation. And they will also produce 2 electrons, 1 for each of the reactions that happened. Therefore, if we take a look at this, the reaction that has electrons as reactants, that's the reduction. And the reaction that has the electrons as products is the oxidation. We can also do these types of electrolysis reactions with dissolved salts, or electrolytes. A classic example would be the electrolysis of sodium chloride dissolved in water. This reaction will split up to produce hydrogen gas and chlorine gas. Now you're probably wondering, well, how did the hydrogen get in there? You need to remember that as soon as something is dissolved in water, you have H+ ions and OH- ions that are present. And it turns out that if any metal is more reactive than hydrogen, hydrogen will be formed. If the metal is less reactive than hydrogen, then that metal will be formed. And we would use that principle in order to electroplate something. And that would mean that you'd be coating something in a metal. In order to do that, you need to be producing the solid metal. We know that metals start with a positive charge, and therefore you'll need to provide electrons to this in order to make that solid metal. This would mean that the electrons are a reactant, and so this is the reduction equation. Reduction occurs at the cathode, because that's where electrons are present. The cathode is negatively charged and it will attract those positive metal ions. And so if you would like to electroplate something, you need to hook it up to be the cathode of your reaction. Right, it's time for the supposedly dreaded mole. In our revision topics video, we discussed attitude in terms of revision and studying, and the mole is one of those topics where if you don't have a positive attitude, you may find it more challenging than you need to. If you already know and understand and like the mole, then hopefully this is just a good recap for you. If you don't, I'd like you to put aside any feelings you have about the mole and try and understand it from the little bit of revision that we're going to do here. We are planning to do a full topic on the mole itself and a full video on that, so if you have any questions about moles, please put them down in the comments below and we'll probably include those in our video. So what exactly is a mole? A mole is just a unit of counting. You've used other units of counting in everyday life, I'm sure. You might have used a couple to indicate 2. You might have used a trio, would indicate 3. You probably used a dozen in order to indicate 12. None of these units are very complicated, and you should be able to convert back and forth. If someone said to you 2 dozen, you would right away be able to tell them that's 2 times 12, and therefore 24. You probably would kind of even skip this 2 times 12 bit and be able to tell them that it's 24. You really don't need to do anything more complicated when you're dealing with the mole. The only problem is that the number is slightly more complicated. So 2 moles would be 2 times 6.02 times 10 to the 23. You're not doing anything different, you're just using a much larger number in order to do this calculation. The reason that number is so large is because the atom is so small. And so you need a great number of atoms in order to make up a mole. You can measure a mole of any substance that you find, and the measures of moles of all of the substances on the periodic table have been done. Those become the molar mass, which is the mass of 1 mole. All of this feeds in to some equations. We need to know that the number of moles, usually symbolized by N, is equal to the mass divided by the molar mass. Whenever you're doing this type of equation, make sure that you're analyzing your units so that you are ending up with grams divided by grams per mole, meaning the grams will cancel out and you'll be left with moles. This will apply in the case of stoichiometric calculations. This is a big fancy way of saying we're trying to discover how much was produced or how much was required. Let's go back to the equation we've been using all along of lithium reacting with oxygen in order to produce lithium oxide. Before we do anything else, we need to make sure that this equation is balanced. And in this case, we know that 2 moles or molecules of Li2O were produced. This is a stoichiometric number or multiplier, and that it took 4 moles of lithium atoms to produce that. Let's examine this and say that 3 grams of lithium oxide were produced. We want to know how many grams of lithium metal were used for that. We know that in total, from the law of conservation of mass, there will need to be 3 grams on the reactant side. But we cannot just divide that equally because lithium and oxygen weigh different amounts. And so we need to convert this to moles. I find it helpful to turn this into a table where the top row of your table is mass, the second row of your table is molar mass, and the third row of your table is the number of moles. If you are going down the table, you are going to divide. That would mean that we'd take 3 grams and we'd divide it by the molar mass of lithium oxide, which would mean we need to look up the molar mass of lithium oxide. It would need to be equal to 2 times the molar mass of lithium plus 1 of the molar mass of oxygen. You can find these masses on your periodic table. In this case, it gives a total molar mass of 29.8 grams per mole. This gives us 0.100 moles of lithium oxide that were produced. Notice that we haven't dealt with this 2 yet. Now is the time to deal with it. We need to understand that this is a ratio of moles. 4 moles of lithium make 2 moles of lithium oxide. We haven't made 2 moles of lithium oxide, We need to figure out how many moles of lithium we actually use to do this. In order to do that, you will multiply across by the ratio of the unknown divided by the known. In this case, the unknown is lithium, and there were 4 moles of that for every 2 moles of the compound that we do know. And so we will multiply our 0.1 by 4 over 2. This will mean that we have 0.2 moles of lithium that were required in order to make 0.1 moles of lithium oxide. Now we need to use the molar mass of lithium, 6.9 grams per mole, to discover the mass of lithium. If we're going up the table, we need to do the opposite of what we did going down, and therefore we need to multiply. So we're going to take our 0.2 and we'll multiply it by 6.9 grams for every mole. This will give us a final answer of 1.38 grams. Hopefully that has covered your questions for the C3 topic. As always, if you have extras, please put those down in the comments below. There's a worksheet with some practice questions for you to do, and the answers to that will be up next week. Until then, happy sciencing.